Ahoy mateys, 'tis I, Monaco, coming to you with our 7th homework lecture on the periodic table. We're hitting up the allotropes. This is a single vocab term assignment, a single page and no real related practice because it is just a fact that you have to internalize here. Because certain elements can take on special forms. This is page 22 in our unit pack. So an allotrope is special. Okay, you're gonna have to squeeze these notes in before you do a little reading assignment. Each of two or more physical forms of an element can exist. So elements can exist in different forms, and that's what an allotrope is. It's a blanket term that describes the fact that an element like carbon or sulfur or oxygen can be found in different forms. Okay. Now, graphite, charcoal, and diamond are the best go-to examples for allotropes of the element carbon. Diamond is a glass-like mineral, okay? Graphite is a very soft black mineral. Fullerene is something that was made in labs, but it is similar to soccer balls, okay? They're microscopic, all right? Like really, really tiny, on the order of atoms and stuff. Well, bigger than atoms, but very small anyways. And then soot, like the black soot candle stuff that comes off of a tailpipe or something, is also carbon. So all these things are made out of the element carbon, but they are obviously very, very different because the way the atoms are arranged. Different arrangement of atoms is why they have different properties. Okay, if you put your building blocks together in a certain way, if you want to think Legos, if I give you a bin of all black 4-dot Legos, you could make a ton of different stuff. And the way that you connect those Legos determines on what you make and how strong it is and its properties. So allotropes are made of a single element. The element is always the same, and the arrangement of those atoms is what varies, leading to those different physical properties. In a diamond, they're all connected very closely. In graphite, they're connected extremely loosely in sheets. In soot, they're kind of just random carbon atoms. Okay, you wouldn't want to build a building out of soot. It wouldn't stand up. If you had enough diamond on the planet, you might be able to build a building out of diamond I-beams. I mean, that'd be amazing. I think potentially it could be one of the strongest things ever. But we don't have diamonds that big yet. Can't make them in labs. So examples, oxygen O2 and oxygen O3. O2 is what we breathe. It's an element, so this is what we breathe. Plants make it through their cellular respiration. We use it through our cellular respiration. Ozone is a different version of oxygen. It actually has 3 oxygen atoms connected together, and this stuff protects the, what type is the term? The stratosphere? The troposphere? It protects the atmosphere of our planet from solar radiation. It absorbs all that dangerous radiation that would hurt life on our planet. So both are oxygen, ozone being the allotrope of oxygen, O2 and O3 are their allotropes, is got different properties and different uses. Sulfur, that yellowish mineral rock you might have had your hands on in earth science, has multiple different arrangements. There's red sulfur, there's white sulfur, and there's yellow sulfur. I think maybe I'm thinking of phosphorus. Yeah, anyways, that might be the phosphorus I'm thinking of. But either way, the idea is the same. You have 8 sulfur molecules could be arranged in a flat circular dish shape. Or it could be arranged in like a crown type shape, showing a 3-dimensional structure. Each one would have different properties and therefore have a different use. So allotropes are a simple, complex name for something so simple. Your related homework is just going to be a simple Google Classroom. And there's some practice on page 22 to complete, just a little reading assignment, comparing and contrasting. And then we've got the next notes. All right, so thanks for watching. Talk to you later.